University of Bologna. He's going to talk about the Dirichlet space on the bidisk. Nicola, please.
Okay, thanks, Javad. I would like to thank the organizers for the invitation to this intensive period on holomorphic spaces. I had already, how to say, put away some time to come to Toronto, and then COVID came. Okay, so what I'm going to talk is some problems on the Dirichlet space on the bidisk, especially Carlson measures and multipliers. So I'm lucky because Tom just lectured on these topics in the one parameter case, so I'm going to repeat a few things. And there is not much literature on the Dirichlet space on polydisks. There are some papers by Catherine, by the way, by Tom. There is a paper by Kapitanoglu. What is it? Okay, and as harmonic analysts often do, if they have a hammer, everything looks like a hammer, since I worked on Carlson measures, I look at the Dirichlet space on the bidisk from the viewpoint of Carlson measures. Okay, let me. Okay, what I'm going to talk is in a work with Pavel Mozzagliaco, Carl-Michael Perfect, and Giulia Sarfatti, 2018. It's a preprint, and there are some. I mean, there are some novelties, but I think that Wolberg is going to talk it in his colloquium talk. So I will stick to this kind of seminar result of 2018. Okay, well, so let's remind the second. Okay, the Dirichlet space is what this workshop is about. That's the definition. And I just, let me just say that, okay, we can add to take care of constants the Hardy norm, but we can also add anything else, like f of 0 squared. And so the advantage of this is that the reproducing kernel of the Dirichlet space becomes like this. And it's easier in this way to see a geometric property of this reproducing kernel. So if I have 2 points Z and W here in the unit disk, and I consider the geodesic, the hyperbolic geodesic, which is this circle passing through Z and W, I pick the point which is closest to the origin, to 0, let's call it Z wedge W, and then the length of this segment in the hyperbolic metric, which is length with respect to the metric dS square dz square over 1 minus mod z square is comparable to the real part of the reproducing kernel. And this is one of the ways in which hyperbolic geometry and the Dirichlet space somehow get interlaced, and we will see maybe another one later on. Okay, now, okay, this is these are two inequalities Tom already mentioned in his second lecture. So we have, so here the topic, I guess, is Carlson measures. Carlson measures. Okay. And the two inequalities are A, it is the Carlson embedding. Okay, here I consider measures on the closure of the unit disk. Of course, this creates some problem on the boundary, because the boundary values are defined in some sense and not in some other sense, but let me trust me that this can be done kind of naively. So we have the embedding inequality, the integral of mod of squaring the mu is bounded by a constant which I call square bracket mu times the norm of f in the Dirichlet space. And then there is the characterizing condition for inequality A, which is inequality B, which is what Tom lectured about. So in the unit disk, I consider arcs, finitely many arcs, and I consider the respective Carlson measures. And then the inequality is that the measure of the union of these things, including the boundary in this version I'm giving here, is bounded by a constant, which I call double square brackets of mu times the capacity. Okay, here I write 1/2 capacity, thinking of a Ritz 1/2 capacity on the torus or on the real line of the union of these arcs, which is the same as logarithmic capacity for small sets. It's comparable to that. And then let me mention two other inequalities, which I'm going to state, then to explain what they refer to. Okay, for this inequality, we have on the left-hand side, AD, A dyadic, it is the integral on the closure of a tree of sum over all i's belonging to this P of zeta, which is like predecessor. P of zeta is like predecessors of zeta, something which belongs to the tree or the boundary, mod square in the mu tilde, which is something like A in the version, is bounded by square bracket of mu tilde times the little L2 norm of phi, and then some corresponding statement about capacities. Now, this I will repeat this later on. The point is that these four quantities are all equivalent. So the point with these quantities is that these quantities are all comparable. They're comparable. And so the fact that the two constants above are comparable is this theorem of Stegenga, which is highly essentially relies on a strong capacitor inequality, which he modifies from Mazia, theorem of 1980. The fact that the two capacitor inequalities on the right have similar constants, it is implicit in a paper by Benjamin and Perez in stochastic processes, 1984, and it's explicit in several other sources. The fact that the holomorphic and the dyadic inequalities have comparable constants, it's work with Rochberg, Sawyer, myself from 2000 and something. And the fact that the two quantities below are equivalent, which is, okay, we have a constant for the kind of this integral inequality on the left and the constant for this capacitor inequality on the right. The fact that they are comparable can be proved by a kind of caricature of the original proof of Mazia of his isocapacitor inequality or trace inequality and so on and so on. So the relation between mu and mu tilde is something that I'm going to kind of explain now. Okay, now, what are these objects? Okay, so consider the unit disk, which is a picture on the left in polar coordinates with the usual Whitney decomposition. So it's that you divide it in regions which are finer and finer as you move to the boundary. And to each arc, to each boundary arc I, well, dyadic boundary arc I, you can associate the Carlson box, which is this one, and the top half of the Carlson box, which is what I call QI. So this one, that's I, QI, SI. Now, this dyadic construction can be thought of as a tree in which this box Qi is somehow parameterized by this vertex of the tree, or by an edge, if you prefer, and and the boundary points. So the boundary set is this one. It is part of the boundary of the tree. I'm not going to spend many words on that. It's like from the topological viewpoint, it's like a Cantor set. Okay, and so the measure mu tilde is defined in this way. The measure of this vertex I, is by definition the measure mu on the disk of the top half of the Carlson box. Okay, so that's the relation between mu and mu tilde. Okay, and this is kind of the picture which we are going to see again. Now, we still have something to say. What is this predecessor set? So if we have a function phi from the tree defined, let's say, on the edges, two positive reals, okay? Now, to each point zeta here, I associate the predecessor set is the set of all edges going from the first edge, let's say the root edge, to zeta. So this is the predecessor set of zeta. And dually, to each edge alpha, I associate S of alpha, like the Carlson box in the tree, which is everything which is below that. And I define this kind of a Hardy operator, which sums phi over the edges leading to zeta. So I phi of zeta is like an integral. It is the integral between here and here of the function phi. And dually, I star of lambda, if lambda is a measure defined on the boundary, it is lambda of what is below, not of what is above, on the boundary or even in the interior. Anyhow, it's the measure of this part here. Okay, so, and this is now, what is this dyadic capacity I mentioned? The dyadic capacity is this object here. So the dyadic capacity of a subset of T union, well, actually what we need is just the boundary. So I might restrict the definition to the boundary here. The dyadic capacity of a subset of the boundary is the infimum of the little L2 norms, so that the integral of phi is greater or equal than 1 on E, or dually the supremum of the total measure of E squared over the energy of the measure, as the support of lambda is contained in E, where the energy is defined in this way. Now, this maybe looks pretty much unfamiliar, but if I consider, okay, if here is the torus, and I consider this dyadic decomposition of the torus, which means that but for dyadic rationals, a subset of the boundary of the torus, a subset of the torus, E can be, okay, a subset of the torus can be considered as a subset of the boundary of the tree. And the point of Benjamin and Perez, which is also easy to prove, by the way, it is that the logarithmic capacity, or the Bessel-Ritz capacity of E, the classical one, the one defined by Tom yesterday, it is comparable to this dyadic capacity here. Okay. Of course, the countable set of dyadic rationals does not really play any role here. So after this, how to say, explanation, here I copy again So we have a kind of meta theorem putting together several pieces of literature in which we have Carlson measures. This is the Carlson measure side, and this is the capacitory side. Right, and everything is comparable. Okay, so to each Carlson measure inequality corresponds a capacitor inequality, and the capacitor inequalities are pretty much the same, and the same for the Carlson measures inequalities. Great, where here I repeat all of the definition. By the way, what is dyadic in a holomorphic space? Because holomorphic spaces are not very dyadic in a reasonable way. Although there is a paper of Makarov with a dyadic study of conformal mappings from the late 80s, I think. Anyhow, so what's dyadic in a holomorphic space? Okay, I consider a function f on the unit disk, and so the integral, well, the function is the integral of the derivative, and so let's multiply and divide by the distance to the boundary, and so this is like the, well, this is, if I put a mod here, this is the hyperbolic length element, and let's call this phi of q of w, where q of w is like, if w is here, it belongs to some box of the dyadic decomposition. I did the picture here to the left, and so let's call phi of q of w is that. Okay, of course, this is just at the level of metaphor, because phi of q of w, this is a number, and this is a function defined in the box. Okay, so at least at the level of metaphor, f of z can be thought of as the sum over all these edges leading to z. And the integral, okay, so the integral with respect to mu can be written this way. And here, maybe I forgot a mu tilde of q. Okay, pretty much at the level of metaphor. While the Dirichlet semi-norm, if I divide and multiply, and here I get invariant area element, can be written as, well, invariant area element, it means we don't need hyperbolic geometry, it's simply the area of this is pretty much 1, of each box is pretty much 1. And so this becomes pretty much the sum of phi of q square over all possible squares. So so instead of this inequality here, we can consider this inequality here like a toy version of it, and in fact they are equivalent. That's the point. If the fact that they are equivalent, I use duality tricks, some estimates which are not too hard, and you can prove, in fact, that a dyadic inequality is equivalent to the holomorphic embedding. Okay. So what happens with the two parameters? Okay, when we have two parameters, the Dirichlet space on the bi-disk is defined simply as the tensor product of the two copies of the Dirichlet space on the unit disk. Tensor product means here simply that you take products of everything inside. So, okay, if you have a function f of two variables z and w with the Fourier coefficients defined in the, of course, in the bi-disk, the Dirichlet norm, we put the coefficients that Tom showed us, but the product, one for the z variable and one for the n for the w variable, which can be written in terms of integrals as a main term in which we take the product of the derivative, the tensor product, let's say, of these two derivatives, which is the derivative with zw, with respect to z, with respect to w, and then area measure, plus mixed terms. So if you want the hardy things, you will put a term where there is a Dirichlet with respect to Z and a hardy with respect to W. And then you have hardy with respect to Z, Dirichlet with respect to W, and then hardy. So you get 4 terms. So kind of part of this, I think, is that you always have some 4 terms to deal with, which is not a great problem. And this somehow has to do with the bi-disk. Okay, so if this is the disk with the boundary here, which is the torus, okay, I'm just taking 1 dimension less. So the bi-disk is this one, and we get okay, the product of the torus. And about dimensions, the disk has dimension 2, so here you are working dimension 4. On the boundary, you have dimension 3, but most of the action takes place here in dimension 2, which is called the distinguish or Shilov boundary of the boundary. Okay. Of the disk. Reproducing kernel is simply the product of 2 copies of a reproducing kernel, and here there is a problem because the product of 2 distances, is not a distance. So that means that, okay, I repeat this later on, but it means that some relationship between geometry and potential theory, which holds if your kernel has to do with some distance, cannot be used in this context. And that's one of the difficulties. Well, and then we have the same tail of the same 4 quantities. Okay, so we have the Carlson measure. Okay, we have a Carlson measure estimate, which says that given a measure mu, defined on the closure or on the distinguished boundary of the unit disk, the integral of mod S square in the mu is bounded by the Dirichlet norm of F, the one defined before. And I call the constant the same way. Then we have a capacitory condition. Which is that the measure of the union for J, which goes from 1 to n, of the Carlson boxes defined on Rj, is bounded by a constant times the capacity of the union of these Rj's. I changed the ladder, and then I draw the picture below. And then here I put dyadic versions of the same. Okay, I mean, I'm not spending much time in this because they're written exactly the same way. And then by pictures, we see what these objects are. And the theorem in this paper with Mazzogliaco, Perfect, and Sarfatti is the same as before. So that all of these 4 quantities are equivalent. Of course, for people in complex analysis, what we're interested in is the equivalence between these 2 things. The point is that we don't have a direct way to do this, and so the way we do is showing that these are equivalent, and then these are equivalent, and then these are equivalent to get the Stegenga results. Okay, so about capacity. So what are these Rj's? So Rj's. Wait a second, here there is a mistake in the picture. Maybe it's a J. So I consider, since I'm working on the product of 2 one-dimensional tori, I have to consider products of arcs on the bitorus. That's it. Okay. So these RJs are rectangles, in fact, on the bitorus. And so the union of rectangles looks like this, and that does not really, you see from the picture, it does not really look like the union of arcs on the boundary of the torus. It's a bit more complicated. This is a kind of a headache also for the Hardy space on the bitorus. And this capacity is defined as the logarithmic capacity, but using the... Okay. It's not a question, I guess.
No, no. Please mute your microphone. I mean, whoever.
Okay, no problem. It was a question in a language I couldn't understand. Okay, and and so the definition of capacity is like definition of logarithmic capacity by using the product of kernels. And by the way, I just found out a few minutes ago that this definition of capacity is also in a paper of Catherine, 2015, I think, and the collaborators. Okay, right. So this is the, so instead of, okay, so we use this to define logarithmic capacity of arcs on a torus, and we use the product of these two kernels to define the capacity of unions of rectangles in the bitorus. And the same picture you get on 3 and by 3. So you have a dyadic capacity, which was defined in this context here. And then you have a dyadic capacity, which is defined in this product constant context here, in which you have this kind of boundary arcs, so to speak, on the boundary of 3 boundary arcs here, and you take the product of these boundary arcs, and then you get unions of rectangles in this Cantor set type object. Okay, so one of the headaches of these things is that when you are in this in this biparameter situation with product of tori or trees boundaries and so on and so on, okay, the product of 2 trees is not a tree, is very far from being a tree, and that you can easily see that if you have a dyadic arc I, the only thing you can do is, well, when you try to make it larger, the only thing you can do is to double it. And then you make it double it, and so on and so on. So you get just one direction. But if you have a dyadic rectangle, you can double it in one direction, or you can double it in the other direction. And then you can, this blue rectangle, you can double it to get like this, and this red rectangle, you can double it to get like this. And so you have 2 ways to get to the original rectangle, to this rectangle here, which is like a loop of this sort. And so when you work on this by 3, you are full of loops. That's okay. Now let me mention some sample applications of all these, and here I will go a bit fast because Tom said everything 2 hours ago. So in the one parameter case, so I talk about multipliers, right? The Stegengels result. In the one parameter case, we consider the multiplication operator on the Dirichlet space, multiplication times b, and what is the norm of this multiplication operator, or let's see, what is the condition on holomorphic b so that multiplication times b is bounded on the Dirichlet space. In the one parameter case, as we learned a couple of hours ago, the norm of the multiplication operator as a bounded operator is given by this, which simply depends on the fact that we are in a reproducing kernel Hilbert space, plus the Carlson measure norm of this measure here. Okay. So in the two-parameter case, where we have the usual headache, so the norm of the multiplication operator is given by this because there is a reproducing kernel, and then there is a main part, which is given by mixed derivative zw of b mod square in the area with respect to both variable, Carlson measure norm on the by disk. Plus, and then you get for the boundary terms, okay, you freeze the w variable, and then you consider the derivative with respect to z mod square, the area z, and you consider the Carlson measure norm in the unit disk, in the Dirichlet, for the unit disk of this, and then you take the supremum over all w's, and you do just a switching coordinates in the other term. Okay, and that's a characterization of multipliers that putting together Stegenga plus this new Stegenga gives you, at least in principle, a characterization of multipliers. Although using these, I'm not sure it's very easy. Then there is some classical thing that Tom mentioned yesterday. So consider a radial variation. So in one parameter, the radial variation of the function f is simply the length. Okay. It is the length of the image of an arc starting at the origin, which may be length of this. Okay, and consider this new inequality for which I use different brackets. So the integral on the closure of the unit disk of the variation of f square, which is bigger than mod f square, right? In the mu is bounded by the Dirichlet norm of f. Well, it is known, actually it is implicit in this Berlin paper, Berlin 1940 plus Stegenga, let's say. It is implicit that these two quantities are equivalent. In fact, from this inequality, you get that the set of boundary points on which the variation is infinite has vanishing, has null capacity. So in two parameters, using the result with Pavel and the others, you can show pretty much the same. Well, you define, you have to define the variation. In the variation, it's less geometric. There is a geometric interpretation, but it's less geometric because the main term is a derivative with respect to z with respect to w plus other terms which okay, are kind of predictable, and we get, and then this is the inequality for the variation for this measure mu, which is the same as the Carlson inequality. Okay, and okay, and I think this probably could lead to say more about exceptional sets for functions in the Dirichlet space by disk, but we didn't work on that. We tried to move in some other directions. Okay, and let me just say something about comparison with the hard space case. So Alice Cheng, 1979, I think it was her thesis. She considered this Carlson measure inequality here. So one has a function which is biharmonic on the by disk, and wants the integral of mod u square with respect to a measure mu to be bounded by the H2 norm of u. Now, the best constant you can put here is comparable to this Carlson type condition. And this is really a Carlson type condition. Carlson type. Okay, that you pick rectangles on the distinguished boundary, which is on the bitorus, and you consider the union of the Carlson boxes. The Carlson box built on this is simply the product of the two Carlson boxes, so it is a four-dimensional object. You consider the measure of the union of these Carlson boxes, and this has to be bounded by a constant times the area of the union of these rectangles. And this is pretty much the same picture we had above, although the similarity is deceptive, because what one expects following Carlson 1962 or 60, okay, here I think the correct date is the one given by Tom, 62. Following Carlson 1962, one would expect one rectangle to be enough. But actually, the same Carlson in 1974 used some ideas from dynamical systems, of a very clever proof, to show that one rectangle is not enough, and that you need and so Alice Cheng came with unions of rectangles, and that's enough. By the way, the characterization of this inequality here, it is still open for the holomorphic space. This is a major problem, and maybe Wolber will say something about it. Major problem in the area. Okay. Now, okay. By the way, this. So over the years, I got this impression that the Hardy space is easier for a few things. Okay, it is easy because on the boundary you have to use measure theory and not potential theory. You have Lebesgue measure instead of capacity. It is more comfortable because you have Blaschke products, and on Dirichlet spaces you don't have Blaschke products. But as soon as you leave complex dimension 1, and you have no more Blaschke products, and you don't have well, you don't have Blaschke products, in fact. Then the Hardy space becomes the least natural space somehow, and the Dirichlet space maintains many of its features. That's because this logarithm keeps things very separated, and you can do constructions even without products. In fact, you cannot use products to do constructions, but the constructions you do in the unit disk, somehow you can modify them to get to the unit ball or the bidisk or so on. Okay, so let me just close with some ideas from the proof. Here I'm repeating, so for a function phi defined from the tree to positive reals, we had this Hardy operator here, which is sum on predecessors. That's like a predecessor set. And we have here we have measure, the dual operator is measure of successor set. Now, following general potential theory, something one can find in, for instance, Adam's Hedberg book, okay, one can define a potential, linear potential. It is I of I star of mu of x. This is the potential of generated by the charge distribution mu at x. In fact, it comes exactly from electrostatics. This fact, you have a charge distribution mu on some conductor, and you compute kind of with the what to say with the right operator. You compute the g of g star of mu, and then you get the electric potential at the point x in space. And the capacity, if you remember, we had this definition here. Okay, and this was it is kind of the picture. Now, in the two-parameter case, let me skip on this. We give pretty much the same definitions. Same definitions. I just double. Okay, so double I phi. If I have a function phi defined on the by tree with value in R plus, this double I phi computed x y is phi of alpha beta, where you are in with alpha in predecessor of x and beta predecessor of y. And then you do the same with this I star operator, and then you get the electrostatic potential, so to speak, defined in this way, and you define a capacity. And for many properties of these things, you just read Adams and Ebert, and you find equilibrium measures and equilibrium potentials and everything. Now, what are the obstructions? So obstructions are these. Well, these logarithmic capacities can be defined as differently as Ritz capacities. So these are capacities associated to Ritz kernels of this kind, where SU belong on the torus, or on 0, 1. So torus. Okay. Now, the fact is that when you consider the reciprocal of the kernel, this is pretty much a distance. When you go in the two-parameter case, you take the product of tensor product, which is the product of copies of the kernel, and the reciprocal is not a distance anymore. So essentially, many chapters of the theory get lost. Another problem I mentioned before it is that the by tree is not a tree. Okay. Now, what is the key element? So the key element Stegenga and we used. So the key ingredient is a strong capacitor inequality. Strong capacitor inequality, okay, I write the one for the by tree, but they all look the same. So I pick my operator, the one I use to define a capacity. Now, the capacity, if I consider the capacity of the set where I phi is bigger than 2 to the k times 2 to the k, and then I sum from minus infinity to plus infinity, this is bounded by the norm, little L2 norm of phi. Right. Of such capacitor inequalities, now this is called the strong capacitor inequality, because the weak capacitor inequality, it is that the capacity, this. So if I remove the sum, well, actually with constant 1, L2 of t squared, okay, and this follows immediately. If you think about it for a couple of minutes or even less, this follows immediately from the definition of capacity, because this I can take it here. This I can take it here. So here what I'm saying is that the capacity where I of a function psi is greater than 1 is bounded by the little L2 norm of psi, which is a definition of capacity. Okay, and it is a few lines showing that strong capacitor inequality implies a Carlson type trace. Trace is the language used in PDEs by people like Mazia, for instance, and the Carlson type by us in complex spaces. inequality. That's a few lines, and I'm not going to spend much about it. I just mentioned that there are two streams of literature on this. The first proof is given by Mazia using gradients. And the proof is of the original inequality and several of its extensions is a few lines. So what was clever is that Mazia thought about it. And then he wrote a proof of half a page, 1 page, let's say. And then there is a proof using potentials by Adams with several extensions and so on by Hanson and others. And this is more difficult somehow, but it works also for fractional spaces, for instance, in much more general. Even when you have no notion of derivative, this proof of Adams works. Now, to prove a strong capacitor inequality, one has a reasonable wish. The reasonable wish is to have a kind of maximum principle, which is called in literature, it's called differently, it's called a boundedness principle, which says that I have a conductor K, I have a measure mu on K, and I consider the electric potential generated by this measure. What I expect, it is that the potential of the measure at X here, where X is not on the conductor, it is less or equal, maybe a constant, but of course in real life constant is 1, as the supremum of the potential on the support of the measure. Right. So if the charge is, say, in Toronto, I expect here in Bologna to have no problems with the potentials and jumps of potentials. I expect potential to be very small. Okay, this fails for d by 3. So you can find a set K in the distinguished boundary so that the potential of the equilibrium measure even of K computed at X is much larger than the supremum of the potential on the support of mu K, which is, by the way, since this is the equilibrium measure, that's 1. So you can find a very large thing. So we back up, and then I'm going to close. Instead of, okay, since this maximum principle phase, so we prove the distributional maximum principle. And this distributional maximum principle says that, okay, maybe there is a non-empty set where the equilibrium potential is very large, and here is very large. Okay, but the capacity of this set is small, which is it's bounded by the capacity of the full set K over lambda. As lambda goes to infinity, this goes to 0. Okay, this works in the 2. Then Mozoliakov, Wolberg, and others worked out the 3. And so, and this is wide open before. Of course, one would like to have the n. And okay, so I do like this. I just mentioned that. Okay, mixed derivative and lack of maximum principle makes one think of the wave operator, and so it's on the back of my mind if there is some relation with the wave operator. These things. Okay, well, thanks. I'm sorry for taking 2 minutes over time.
Thank you very much, Nicola. Let's thank the speaker. And is there any question or comments for Nicola? Okay. I do not.
Well, then I'll
Yeah.
ask you a question.
Please.
May I?
Sure.
Please.
Nicola, do you have a version of, or do you use a version of Carlson formula for the Dirichlet integral to look at the capacity? So there is
No,
Is
that's
it-
no, that's an interesting. No, we didn't.
okay, because you
At the very
mentioned
beginning, we discretized everything.
okay.
And then the problem becomes combinatorial. But that's a very interesting idea.
Okay.
I think basically everything Tom has mentioned so far on the ByDisk is wide open for the Dirichlet space.
Okay, thank you.
One of the things I didn't understand well, when you define V of f, the length of this curve from point Z to the boundary,
Right.
does this mean that V is identically 0 on the boundary?
No, when I defined, wait a second, I'll get it.
Because you go from zeta to the boundary, but if zeta is already on the boundary.
No, you mean the radial variation, right?
Yes, yeah.
Yeah, the radial variation, by the way, that's in this, I think it was defined first in this paper by Burning in 1940. What is one parameter?
Yeah, here.
You take the integral from 0 to 1.
From 0 to, but
From 0 to 1 here. So what you're doing is you are considering the length of the image of, you consider this segment. Okay, it has an image under F, and you consider the length of the image. Now, in the Hardy space, the radial variation can be infinite, almost everywhere. There are examples by Rudin. Then there is a lot of very sophisticated work to improve this. So anyhow, on the Hardy space, yeah, radial variation is not a useful, how to say. You cannot say many things, right? On the Dirichlet space, there is this Burning result, saying that from the viewpoint of boundary values, radial variation is pretty much like boundary values. In fact. You have boundary values if and only if you have finite radial variation, but for a set of zero capacity. That's the statement. Yes.
It's clear. I mean, I thought that you go from zeta to the boundary. No, you go from 0 to zeta.
From zero. Yes.
Yeah. Okay, thank you. Any further comments or questions? So let's thank Nicola again.
Thank to you.
Doing it. We come back